Today we are starting with DUBRAVKO. DUBRAVKO CULIBRK, who is from around here. DUBRAVKO is an academic and a researcher, and he is the head of the Serbian AI Institute. DUBRAVKO, would you mind joining us here?
Hey guys.
Welcome, DUBRAVKO. And in case you were not aware, we can also refer to DUBRAVKO as Your Excellency.
Oh no.
No?
No.
Ah, so
it's
you're
just
not
academic ambassador.
But you are not. I understood you were an ambassador, but to
Yes.
ambassadors you do like Your Excellency, no?
Absolutely, when they're sponsored by the state. When it's just NVIDIA and a corp, then it's kind of a little bit.
So when it's sponsored by the corporation, it's like, dude, what's up?
Yeah, dude, what's up?
Okay, great. DUBRAVKO, you'll be talking to us today about?
We'll be talking about large language models, which is like all the hype, I guess, in AI these days. But increasingly, they've begun to be used as code generation tools. And because you guys are all agile, I'm thinking that maybe this is something that you should take a look at in terms of, doing things faster, but also be kind of aware of all the debugging that you need to do afterwards.
So very relevant and very up-to-date topic. Now, DUBRAVKO, yesterday we had one of the speakers, so we asked them obviously about like the more interesting things about them. One of our speakers was a free diver yesterday with his own personal record of 21 meters.
Right.
I understand you also do some diving, but not free diving?
No, absolutely not. Like 21 meters is way above what I can do. But I do a little bit of scuba diving, not as much as I would like to. I do more snowboarding.
Oh, that's cool.
Which is kind of weird. I started late, like 29 years old. So like it's not, and I'm not really built for it, right? When you look at me, it's not Shaun White, right?
You should be doing basketball, I suppose.
I guess, yeah. It's not so much fun.
Good. DUBRAVKO, I'll let you with our audience. Audience, I'm leaving DUBRAVKO in your hands. Be thoughtful, be mindful. Everybody here around has feelings. We learned that yesterday. Make sure to ask your questions in the Match About app. DUBRAVKO will leave the last 10 minutes of his presentation to discuss your questions. And if you don't manage to address every question during the session here, we'll be able to catch up with DUBRAVKO later during the coffee break. Enjoy.
Perfect, thanks. Let me start this up, if I can. I absolutely did not rehearse this, so I finished the slide yesterday. So the first thing is sort of a disclaimer. Why am I doing this today and talking about this? And if I can manage to flip. Actually, when I started my career, I did my undergrad here in Novi Sad at the Faculty of Technical Sciences. I was a computer engineer, and at that time it was merged with control system major. And my first job was part-time assistant at the faculty, part-time working for a company, development company in Novi Sad. And we were actually building compilers, right? And even then, it was, so we're talking 2000, right? Compilers were fairly old school stuff, unless you had some quirky hardware that was not supported by anything else, right? And at the time, electronics were not as great as today, right? So just playing an MP3 and playing some music required, a specific hardware designed for that to be able to cope and, not run out of battery in 3.2 seconds, right? So we had to do that. So it kind of stuck. After that, I completely moved away from this, right? And I went to Florida to get my PhD, again in computer engineering. But when I got there, I said, so what do you do? My supervisor asked me, and I said, I'm doing code and compilers and things like that. Oh, that's so old school, dude. We're going to be doing images, right? and so I got into computer vision, which sort of is a gateway technology, it turned out, towards developing more general machine learning AI systems, right? So I guess everybody hear chats with GPT these days. At least there has to be a large language model that is the most famous, right? I was listening to the radio the other day. I think Webster's or somebody said that the term of this year is artificial intelligence, which means that everybody's talking about it. But how many people here actually know what the GPT stands for? It's too hard to see. Either you guys are shy or which I understand, engineers, right? I think GPT for me, actually, if I can do this, wrong side. See, not good. All right. To me, that's sort of an engineer's dream, right? When I was even in like grammar school, the only thing I really hated was generating, essays for my language classes, right? For literature courses. Everything else, maths, I loved everything. But like sitting down and writing how I spent my summer was horrible. So I think that's why we built GPT, right? the pre-trained transformer bit is a little bit non-intuitive, but I guess as we go along, I'll try to explain why this happens, right, and why we call it that. But more importantly for me is whether you chat with this guy, right? Well, it's just not to type. I guess everybody knows here, if you are agile and developers, you know about this guy, right? You're a tough audience. All right. Go.
Maybe they're not developed anymore.
Come on, dude. It's just it's a chat engine, right? It's not like everything you do is completely your own creation and you never went to Stack Overflow, right? Come on. We share knowledge, right? It might be easier to share it and to get a template now, but it's not that all developers grew up in isolation and came up with this themselves, right? When I was starting to program, like Cunningham and Ritchie were all the rage, right? So nobody knows who they are anymore. But there you go. There's some old people here as well, right? And but let me take you back a little bit to how we got here. And hopefully that gives you an idea of what's going on underneath and maybe sheds a little bit of sort of intuition of what the limitations of these systems are and how likely they are to replace anything or what they're going to be replacing. I have way too many slides. I was kind of worried that I'm going to go through them too fast. so we'll brush to some of them, right? But so it's not that artificial intelligence, although everybody wants to say this, right? And you'll see a slide from NVIDIA here that claims this outrageously. It's not so far away from your basic computer programming in terms of that why you built computers and why you started programming is to make computers do some tasks that usually people do, right? Or they used to do, right? And you want to help out, right? And so early on, it was basically all we could do is program, right? And although we looked at how like our brain functions and how the brain of primates and then lower organism functions, we couldn't really do much with the electronics we had at our disposal at the time. So in the 50s, the classical computer von Neumann architecture won, right? And it's been around for a long time. And then if you do it on a classical computer, then basically what you can do is figure out how to program a computer to do what a human does, right? And then usually you would want to program a knowledge of somebody who's fairly expensive and hard to educate and so on. So you might want to program, I don't know, a helicopter pilot or a doctor who can do some sort of decisions and so on. And this was like a grind, right? You would come up with the rules, you would represent characteristics of something, and then you would just program how this is going to work. The good part of it, with reasonable, everybody's a developer or does software, with reasonable certainty you could kind of figure out what this thing does, right? there was always, there's some uncertainty, but there are errors. But there are some things that we really struggle to do, and this is actually what's been sort of the core of my research for a decade. You guys all know computers, which makes it a little bit easier to talk to you, right? So, how am I going to get from that pixel and these millions of pixels in 3 colors, right, to kind of understanding that there's a cat with the little white flowers, and maybe you can count the flowers, and there's some, it's blurry, there's some grass in the picture and so on. So it proved that for ages we were trying to figure out smart ways of representing these relationships between the pixels, right? And these patterns kind of transcend this media. So you could do this for text, right? You kind of represent the relationship between first the characters, then engrams, which are basically just a few characters, then something bigger, and you should get some sort of a sense out of it, right? And it proved that designing this could do some things. So, we could do a fairly decent search engine or Google rank, right? But not much else, right? And so the idea of machine learning is fairly simple, which is, people can learn by you showing them an example, right? and telling them, okay, dude, that's it, or that's not it, right? And so we tried in various ways to do this, right? And to create sort of small algorithms that basically define how we're going to represent this knowledge, right? And how to adjust the parameters of the algorithm. And then once it's done, you would just take a data set of examples, and we're talking supervised, but it doesn't matter. That's the get-go thing and the basic of it. You would show an example to this algorithm, tell him if it's wrong, it's not wrong, and kind of adjust it so that you get something that could make a decision, right? And this brings us actually to one of the most important questions in machine learning today, which is basically this. What does a cow drink? And not what you thought second, but what you thought first. Yeah, I mean, arguably when it's little, it does drink the milk, right? But there is such a strong association between the cow and the milk that nobody's going to tell you. I mean, if they say they thought water on the first go, then that's a weird guy, you don't want to deal with him. Right. But it's actually, I borrowed this from a psychologist friend of mine who also does data science and so on. And it illustrates, so what we're doing here in this sort of learning, and you'll see through the presentation, and maybe later we can talk, it's something that it's usually called associative learning. And this helps us react really fast, make decisions really fast in a critical situation and so on. But there is a certain layer behind that we call symbolic reasoning that humans do, right? But AI today does not do that, right? So we're at the level of this, scaled up to thousands of examples, and then we get a sort of a semblance that there is something deeper going on, which it's dangerous only if you really think that it is, right? because then you don't know, then you trust these decisions way more than you should. We had a little paper like 10 years ago. It was super funny. A psychologist made me do it. I thought it was super stupid. But we got students to kind of do basic math tasks, and you would get a sort of a sound if you did it right or wrong, right? But the computer was judging. And we showed that so we messed with half of them, right? So you would do right, you would say 2 + 2 is 4, and then the computer would emit the sound that you're wrong. People got super stressed out. I mean, stressed out within 10 minutes so that you could, in evaluation charts really get it, because they could not believe that this thing is lying, right? And that is sort of a problem that we have with AI today. I mean, with the internet, with everything. We trust the machines more than we do ourselves. It's a human thing, right? so that's where the danger, I think, lies, right? Okay, so how are we actually, what is the basic kind of directions that everybody's working on? And it has been working on for a while, it's just now there's leaps and bounds and so on. So recommender systems, great, the money was there. It was sort of without the internet and a lot of data, they were not even so interesting, right? So there was a sort of a perfect trinity of the things that you could do. It was a green field. We did a lot with that. They're getting better, of course. The part that we were really, maybe 10 years ago, struggling with without these big neural nets that we do these days, you couldn't basically do decent voice recognition. I mean, you could do, play, stop, whatever, 70% accuracy thingy. But we learned quickly with these systems, because when you're programming, there's a certain error of the system that people are used to tolerating, but it's a bug that happens every once in a while, right? But if you have a computer system that is sort of making recommendations or doing decisions or something like that, that is, wrong 30% of the time, it's just meaningless. It's useless. People don't want to use it. Right? So there's almost for every machine learning system, there's a sort of not a set, but there is a clear limit to the performance that is acceptable to the humans, right? And this is 10 years ago, we started kind of breaking this in a lot of the problems that we were solving. Another problem that we were kind of solving, of course, is the computer vision stuff, which, 15 years ago, cameras did not even recognize your face I don't know, nobody remembers that, I guess. There was no way on a digital, let's say, camera to have your face, focused on or detected and so on. Now they can do all sorts of things. Right? Easily, not a problem at all. But a lot of it has been driven by these self-driving cars, because they need to do a lot in terms of recognizing the objects around, and it's a fairly unconstrained problem, right? And also robotics, because we know how to it's easy to move the robot. We know this for a long time, right? It's just that because we could not understand what's going on around it, then we kind of tried to constrain it. We were better at moving it than understanding what it needs to pick up, right? So you would kind of calculate the precise movement. If you knew that this was here, then if something moves, it's done, right? So computer vision really helped in that. And then the last but not least, I guess all of you guys know that now playing chess with a computer is kind of super weird. For me, it's one of the nice things when we do things with machine learning is sometimes we get, well, it's also a bad thing, but a good thing. Sometimes we get interesting results that are not bad for you, right? So actually, a friend of mine is really big on chess, right? And he told me, like, the world champion chess player kind of said that since we were doing this reinforcement learning, which was highly coupled with the advancement of neural nets and so on, and it's basically how you train something to perform a strategy of movements, not just one decision, but you need a sort of a whole strategy before you can figure out if this is going to be successful, right? And these days, the chess champion actually loves looking at how these things play chess. Because when you grow up as a chess player, there are certain things you never do, right? You're not allowed. If you do this, you know, your teacher is going to tell you that you are insane and that nobody does that and you cannot do this and so on. And then, but the computer doesn't know this, right? It explores the different combinations and so on. So it opened up a whole set of new strategies, crazy strategies that are super interesting to humans now, right? Because this thing is sort of, it's human as much as a submarine is a whale, right? It does some things that you can do, right? Cannot do a lot of things that you can do, right? But it's not the same, you know, it does it kind of weirdly. All right, so why now? Why this last 10 years? Well, there's a sort of, you need three things, and everybody knows this, and we've been talking about this for probably 5 years, so probably you know this. You need a lot of data, right? Which arguably with text, you had a lot of it, right? With images, it was kind of tricky. So, and I'll got to get to the slide to understand why the images were sort of, you know, the first thing that we solved and why this was more important for us. But what you basically need is not a lot of, not just data, but some sort of labels, right? You need kind of you need that part where, show me an example and I'll tell you if it's right. And the right part had to come from a human. Even today, it comes from a human, right? And I know everybody's like, wow, how it's great, and you know, we have ChatGPT, and can you just make me a chat engine that's gonna support reproductive health in young adults in Serbia? And I'm like, dude, there's a $2 an hour guy in Kenya, a lot of them, that has been chatting with this thing for like 2 years before GPT-3, once it was trained, was GPT chat, right? Not to mention the small amount of $1 billion that they got, you know, okay, arguably they spent $5 million on these Kenyan guys or whatnot, but it's not that it just, out of the blue, it does whatever you want. Right? So we still need the data and the labels, but what we really needed also is computing power, right? And now it's old school, but think of it. NVIDIA, who is basically, if you know, especially for the guys that know Cunningham and Ritchie, you know, it was basically a gaming card company, right? Made graphics. Last year they had 101% year-over-year growth, which is, and you know, we're talking multi-billion-dollar company, tens of billions. It's not like, you know, they grew from a really good start. So it turned out that what we really needed to get those neural nets in the 50s going, they needed to be complex. And you'll see, and you know this probably, GPT now has, well, the 3 we know what it had, the 4 nobody knows, like Sam Altman doesn't want to say, right? But it had 175 billion of these weights, connections, whatnot. It's way lower, it's like several orders of magnitude lower than what a human brain has. Not to mention the fact that what we do is a real simplification of the complexity that we have in a biological system. It doesn't mean that, I mean, there's certainly some redundancy, so you cannot really compare that. But to me, a funny thing is, do you even know how many megapixels your eye has? Because, I mean, you buy these cameras that there's, it's 12 megapixels, it's 14 megapixels. Well, I mean, there's no real way to say, but you can kind of estimate, because it not only is a camera, it's pan, tilt, zoom camera that does all these things and so on, but a rough estimate is 576 megapixels, which is still a little bit better than whatever camera you can buy, right? It's not. Every kid has it. Well, I mean, hopefully most kids have it, right? All right, so, and then the catch of the thing, we had these things that were designed to play games, and they're very parallelized architectures, right? And the older guys remember we used to experiment with this. Not that the von Neumann was the only thing that you would do. You would have processors that have a lot of cores doing basic operations and so on. It never really picked up too much until the games, right? Until the money hit why you need this highly parallelized thing. And when you think about it, if you do graphics, I don't know how many people do graphics, but developers do everything, right? Then to do anything with the digital image, right, the model, you basically have tessellations. You have a lot of triangles that you work with. And moving this, marble in space, shading and so on, it's just a matrix multiplication thing. So you don't need a complex thing. You just need to do a lot of the same simple things to a lot of data points, right? And so there is only one algorithm or paradigm that we know that is so suited to this highly parallel nature, and those are the neural nets, right? Everything else is somewhere in the middle. And we knew this in like 2003, when my supervisor told me that, forget compilers, we're going to be doing images. It turned out that at this small university that is not remarkable, Florida Atlantic, they had a lab that at the time had the greatest resolution camera in the world, right? To the point that they were actually supplying to NASA, because NASA wanted to check whether there were cracks in the plating of the space shuttle. They just lost one, right, because of that. And so they were selling this to NASA to be able to examine and zoom in and so on. And at the time, it was sort of a big deal of this 9/11 was still hot, security and so on. So they told us, okay, we're in Florida, there we have like one of the biggest ports in the world, Fort Lauderdale. We're going to stick this on a Navy tower, right? And you just figure out if whatever is moving in this image is something that we should be concerned with, right? And so, sounds great. The problem is, looking at the harbor, there's not anything that doesn't move, right? There's waves, there's even the pixels, we have a wonderful processing in our own brain that makes them look the same, right? If they're not shifting too much. But like if you look at the numbers, it's always shifting, right? And then there's a cloud, then there's a wave, there's something on the beach and so on. So, and the camera was so big that you couldn't even store the image on a hard drive fast enough. You couldn't read out the sensors. So what the guys in the lab would get an FPGA, which was the closest, the fastest thing to an ASIC, right, to do this, because it was all custom built. And so now we need to analyze this image. The only thing we could do is use an FPGA. I don't know, everybody knows what an FPGA is? It's a programmable chip, right? And so what kind of algorithm? Well, let's do a neural net, because nothing else, would have worked. And 15 years later, this kind of grew up. We came to a point that we have GPUs now, and you could do CUDA, and you could do cores and things like that. You can parallelize something extremely on a commercial piece of hardware, right? And this is where we really lucked out. In, both NVIDIA, which I'm just lowly associated with them, but the neural net guys and the machine learning community, right? And now what they want to say is I'm going to slip to that it's flipping traditional programming on its head. Of course it is, because if you had a, why program if you can tell a computer, this is what you have, right? This is what I need you to do, just do it. Right? The problem, of course, is, as with probably some developers, if you do this, it might turn out that you don't even know how exactly they did it, right? I had a small startup I started before the institute and so on, and it's some sort of web conferencing thing that kind of pays attention to your engagement, and hopefully it's going to reduce the stress and so on. And for 2 years they're explaining to me that so the underlying technology is WebRTC, Google Meet. You can do stuff with Google Meet, right? And they're explaining to me that the lag in the system and why it cannot support more than 20 people and something like that is because the model, the AI model that looks at it is slow, that they cannot, they're using the API to get it and so on. You know what it turned out? It turned out that they're sending an image from each of the clients separately to the API. So they're not, they're skipping all of the video coding, just sending iframes and pinging it, image by image, right? So, I mean, the fact that we don't know what these things do, I'm not sure that we know what developers do most of the time. So I'm not too keen on this thing, but it is a fundamental shift, because a lot of the stuff you can now do in an automated way, just by telling it what you want it to do, right? But before we get into what kind of code it can generate and what the accuracies and so on, basically the whole large language model for code generation is as it's is in that sentence. So like the code generation is something that was slapped on top of it, right? you don't, if you look at it, now it's like the GPT-4 code interpreter, whatever that is, right? Why is it a code interpreter? Well, because it can execute some Python code, which, thank God, everybody's doing Python now. Well, let's see, I don't know. But the other part is that, if you're not that good of a coder, maybe you're a good sort of project manager or inspector, right? So now it interprets code. You give it the code, and then it chats with you about how good this code is, and then whether it's well structured and so on. And I had one of my friends who's just, as a hobby, late in the game, he's starting programming in Python and so on. So he inputted this in ChatGPT, and it says, wow, okay, it's well structured, you have all these like variables, it's great and so on. He says, yeah, but it doesn't work. I would like to find it. Oh, excuse me. Never found the bug, right? But it is nice to have somebody to talk to. It's sort of pair programming again, right? you do this thing, See, you did a very good job. You should be proud of yourself. But so there's a lot of things that we do with natural language processing, but the core is that. The core is sort of understanding text, because that helps with recommendation systems, that helps with a lot of things. And then the code generation is sort of, which I don't like personally, but I don't see, there might be a way to do it, but nobody is doing it as far as I know. It kind of, all this computer engineering compiler knowledge that we had, we threw out the window, and we are looking at code as text, right? And then if you look at a lot of code, right, the whole Stack Overflow and everything that is in Common Crawl, right, you get some meaningful things, but it's not, I think, the most efficient way to do this, right? But if we go back to what GPT is, it's a generative pre-trained transformer, right? So the last part is kind of a definition. What a transformer is, it's just a neural net. Right? Before that, the good thing about text is that you don't really need labels to do a lot, right? Because what you always have in text is a sequence of words, right? So there's a sort of almost innate task that you can give it, which is just tell me what's going to happen next, right, in this sequence. And the longer the sequence, then it gets, it becomes a more complex problem. And before transformers, most of it was done by sort of smaller nets, but which had neurons that were fairly more complex, right? They could, forget something, they could do things, and so on. And then at some point, somebody said, okay, let's, dumb this down. Right? Basically, we give it access to all the words in the window that you care about, slap a lot of data at it, and just learn, right? And because if you do it like this, then it doesn't really matter if you're generating the next word, or you can just mask the words in between. So it was no longer, let's say, generated as such, looking to the future. It became something that transforms text, right? Everybody called it a transformer. And, this thing is a little bit different than GPT, but you would be surprised how similar they are, It's just larger, there's a lot of these blocks, and they even simplify it a little bit, but that's it, right? And so then they kind of realized that and DUBRAVKO was the big one, the first one, so on, that was the nature of GPT, and I have not too much time, so I'm gonna, the guys told me that this is gonna work, but it's not. It turned out that these things are super heavy to train. There's a lot of data that you need, and like the first, let's say, GPT-3 run was like $100 million, right, in server time, right? So that's a lot. Right? So what we now try to do is sort of figure out ways in which you don't have to use that all the time, right? And you can. So it learns sort of to transform text, but then at some lower levels, you can extract sort of a representation of the text and do different things. So you could do, put a query in, you get a representation, this crazy multidimensional space, but it's just a vector or a matrix of numbers, nothing else, right? And then do that for the answer, and you can then basically cluster the queries and the answers and get a decent machine learning model that will answer good questions for you, right? Or provide good answers for you. But you don't have to train the whole thing, right? You just train on a subset of the things. You still need a subset of this is the question, this is a good answer for me, right? But it's not, it doesn't have to be all of the internet plus something. And I think I don't have the time, so I'm not gonna go through that. But in the end, it's super simple. Like every of these neurons, right? It's not even the neuron that counts. It basically has the connection, which is something that you worry about. It's a number, right? Usually it has another number that you add to that for various reasons. So you have basically 2 parameters per neuron that you can train, right? And if you look at it from the simple standpoint, it's completely equivalent to, let's say, fitting a line through 2 points, right? Because you basically have like 2 parameters that you need to fix. And this is what we do all the time. Like we do it for 175 billion of these connections, but it doesn't really change the nature of it, right? And the way we do it is the simplest And the craziest way, which is basically, if you can kind of calculate an error in some way, which for a line it's quite easy. You can look at, a square error which gives you the distance of the points from your line and things like that. Then you can try to adjust a little bit this. And for programmers, they hate maths. So usually we have like Python code on the side to help people understand what's going on, right? It's ridiculous, but it is what it is, right? When I have this, then I know how to move, right? And there's if I were to plot this for all the values of this M and B, right, you would get a sort of a shape, right? And where you want to be is sort of where the blue thing is, where the minimum of the error is, right? And so if you were to look at it in 3D, it's sort of a bowl, right? Well, I mean, if it's a bowl, it's great, then it's easy to solve. If you have a lot of neurons, then it's a little bit. But it boils down to the fact you're on a mountain, and you want to get to the lake. And the lake is where the lowest part of this valley is, right? And so what we do, but unfortunately, it's not a clear day. So you can see only maybe 2 meters around. So you're on this thing and you look, okay, this is where it's going down, I'm going there. And that's gradient descent. And this is what we do all day, right? But if you do it all the time, then you get there. And then there are some things that you need to kind of know if you're training these things and so on. First of all, how big of a step am I going to do, right? That kind of defines how fast I'm going to go there. But because I kind of see only the points that I stand on, then if the step is too great, if I'm a giant, I might just go over the value, right? So that thing is kind of important, right? The other thing, which is basically the learning rate, right? Then to do sort of smarter things, we give it momentum. So if I'm really going well, then I'm going to increase my stride. If I'm kind of stuck and it's tough, I'm going to lower the speed at which I'm walking and things like that. And finally, somebody said, okay, I mean, it's great. I can understand that I'm not going to look at all the documents on the internet to figure out where exactly to go, right? But do we really have to do one? So in the end, basically what we're going to do is maybe 64 examples or 32 or something. And programmers, it's called a batch, right? Just like a batch file is a batch. So these are the basic things that control our learning, right? And I'm going to kind of bug you with that. But what I do want to point out that if you look at it in terms of neurons, then these weights, these are the things that we're training. The neuron itself is not really interesting. And the only thing that you need to do, if you can calculate the error at the end, which is basically how far is this from a cat, and there are ways in which we do this, right? You can kind of figure out how much each of these guys contributed, right? So you can adjust sort of a reward to each of the weights to get them closer to where you want to be, right? We call this backpropagation. It is the stupidest, let's say, algorithm that was found out by a few people in the 80s, right? In the 70s. In the 80s, it was really popularized by Geoff Hinton, who is like the father of deep learning and one of the Turing Award winners. But in the end, it's he hates it. He thinks this is the stupidest way to do things, but we don't have a better way of doing it, and nobody has found it. He's really, really working hard to fix that. Right? All right. There is one thing that you will not, I mean, on such a broad lecture as this, you would not get into it. But there is a thing that kind of happens after everything is gone through the weights and so on, and you calculate the input to the neuron. There is this activation function, the transfer function. Because basically everything that happens in the net, you just sum up the weights times the inputs that came from the previous neuron and just generate the output. But if I were to do this all day, it's just a linear transformation. So the only thing that I could learn in terms of whatever classification function and so on, it's a linear thing, right? Which doesn't really work. Like a lot of the stuff in life are nonlinear. So what we have is a sort of function that basically warps it so that I can get nonlinear things. And the funny thing is that with the old small networks, which were like hundreds of neurons and so on, we had a way more complex transfer function. We had something called the sigmoid, right? Why? Because then with a limited number of points, right, in the space, you could get a fairly continuous complex function, right? But then that had some bad side effects. So when we tried to scale up the networks, it turned out that this was too complex for us, right? So now the function is super simple. If what you sum up comes out to be positive, just pass it through. If it's negative, just clamp it to 0. And this stupid thing works way much better and allows us to train a lot of the things. And the other guy, there was a Hinton student, Jan LeCun, who actually is the chief AI of Meta. His background, he was an aeronautical engineer, right? He was building planes originally. And then he likes to say, it's hard when you look at it. We were looking at how the neurons behave, and the sigmoid function is something that we figured out in, giant squid neurons and things like that. But it's sort of like learning to build a plane by looking at the bird, right? So is the feathers that are important? Is it the flapping of wings? In the end, it turned out that only the aerodynamics of the wing is what you care about, right? But you just don't know this from the start, right? Okay, I was spending way too much time on this, and my timer doesn't work, so hopefully I'll figure out when the time is, right? But this kind of shows you how the models grew in deep learning. So we started in 2012 with AlexNet, which is the first one that could reliably classify 1,000 types of visual objects, right? And it was just 450,000 weights, but at the time, I got from NVIDIA K40 or K20, I think, 2 of them. It took me like 3 weeks running to train it, right? And before that, when they were training it, they had to combine 2 GPUs to even fit the model and so on. And now we have a model that like GPT-3 is in billions, hundreds of billions, and then there are new ones that are getting to trillions, right? Whether this is required or it's a way to go. It has not always been straightforward, even in this AlexNet and in these sort of visual models. We got to the point. We got to the point that where it was not only the number of neurons, you had to do something smarter to get it done, right? And they say I'm like totally over the time, so that's going to be fast. But what I wanted to kind of point out is this. As I said, once you have this big model, which you're not going to spend $100 million to train it, and there are models that are open source, like Meta open source some of their large models, not as big as GPT, but due to some quirks, they're quite comparable. I'll show one for code. Then you can do other things with it, right? like pay the guys in Kenya and get a good chat, and then, you know, have everybody know that you're building this thing, right? But then basically you still need sort of data from and inputs and ranking from the people to get it to do some things that you want to do, right? Now, what you usually don't see in a model is that it's not really that it's a sort of a white lie that we input text into it. We do, but if you've used GPT, then you'll know that they are sort of, they bill you in tokens, not in, you know, characters and words and so on. And so what is it? Well, nobody knows. I mean, you know for a specific model, but for the other one, it might be something else. Why? Because basically, the first thing that we do, we are trying to learn sort of engrams, right? We used to use like 3-letter words or 5-letter, you know, strings and things like that. And then somebody said, okay, don't do this. Let's look at the statistical distribution of the characters, and whatever shows up most, we create that as a token, right? So it really depends on your data set that you're training on, you know. And basically, if you look at the code, it does some things well, but then, you know, you'll have a semicolon and an I together, which no compiler would ever do, right? The reason is basically it's trained on English, a lot of English words, right? And maybe this is a better illustration. If you look at what it does in Serbian, it doesn't really represent any kind of a distribution or normal distribution of our language. So unfortunately, to get it to be meaningful, you kind of need to do a different tokenizer for whatever you're doing. That completely changes the space that the language model is operating in, so you have to train the whole model, right? And that's why we don't, you know, even for code, it's not something meaningful that they do, right? Because, yeah, well, I thought it was going to be too much to say before that, so. But you can ask things, you know, get me a Python code, and with the computer vision background, this is the first thing that came to me. And it shows it, right? I didn't run it, I was too lazy, I have to say. But, you know, and it kind of provides an explanation of what exactly you do and so on. And you can mess with it, right? You can sort of C code, right? And there's like, it would be 10 more slides, so definitely not. More likely than not to work, but like, to me it's interesting that it kind of, even in the explanation, it kind of used a completely different denoising algorithm, right? Because I guess this is what it was the best match that it had in a database and so on. And then you know, I had to do it, right? So I asked it for an assembly code, because when I started out, I actually had to write assembly code for this crazy thing, right? Not x86, but a different architecture. But it's actually going to do that for you. What this does to your computer, nobody knows, right? I mean, I wouldn't even run it, and I don't have a processor to run it, right? I'm on Mac, but so on. So the question where it works is basically how you evaluate this. And so they came up with some sort of benchmarks. And so what you basically do, you either predict sort of code completion, which everybody loves the tab, right? And I always loved it. Either you do code completion, or more likely you'll give it the start and the end of the function, right? And you can either give it just that, or some sort of the description of what you would like to do, right? So there are two classes of codes. And it tries to fill in the code in the middle, right? And then if it runs on the first pass, it passes the unit test, then it's a pass 1. If it generates 10 times something, which it does, it can rank sort of alternatives that are likely or not likely, and there's one that passes, then it's a pass 10, right? And I'm going to be super quick with this, I promise. When you look at the results, so it's a little bit, it's designed for Python. There's like JavaScript. Somebody tried to do this data set in JavaScript. Everything else is super shady and hard to judge. But in 33% of the times, right, you kind of get the code that works, which I think right now it's still not nearly as what we would like, and I think it's not usable, but it is a nice way of, maybe you don't have an idea how to start this, go and get it. I wouldn't do it for a large chunk of code, but something small, and while you're learning, it might be super useful, right? And you can look at this Hugging Face. What's important to say is that this thing, Llama is the Meta's model, which is open source. So you can even fine-tune it on your own data and play around with it and so on. And if you find it hard to do, just let us know, and I'll find you somebody at the Institute who can help, right? So there's not a lot of takeaways, right? But you should pay attention to it. And if you're writing unit tests, this it can do, right? Pretty much. It depends on the unit test, but I think it's going to be easier. You need to kind of pay attention to the tools if you're the developer, right? And maybe think about how much this affects your work, and is it going to speed it up? Is it going to change the way things are done, and so on? And the conclusion, what I would like to say is that these reinforcement things and what makes the ChatGPT smart, the last part, the reinforcement learning thing, started out by basically playing video games, right? And when we started, the first thing that it was doing, it was sort of the whole video game was represented as some sort of pixels, super easy. That you would know where the line is, you would know where this is. It took it 2 hours to beat like the best human players and so on of training. But what happened next was more interesting to me, because they used the advances in computer vision. So now the computer was just given the shot of the screen, and it learned to play the game, right? So now, with the code, we're at the level that it's looking at a lot of code. It's going to be this and that, and you're going to try to modify it to different languages and so on. But maybe at some point, what it's just going to see is, it's going to look at your screen and figure out that, I think you're doing something wrong with this, right? And that's going to be a kind of a changing thing. And the other part is, if you really want a computer that is going to be versatile, and everybody's talking about artificial general AI, which can do all sorts of things and so on, but they're always thinking of an AI that is human-like, right? Why would you need that? As a computer engineer, you need a computer that can do pretty much everything, right? And a computer that can code itself to solve any kind of a problem, that's it. It's not going to be a human general AI thing. It's just going to be a really useful or potentially dangerous computer. So I hope I didn't bore you. And I'm sorry to have run over the time.
Thank you, DUBRAVKO. This has
problem.
been quite amazing. There are actually quite a lot of questions for you, but since we also have quite a lot of coffee, juice, and kiflica outside, may I suggest that you stay on the stage and do the Q&A session like privately, one-on-one, or whatever. We will turn off the big lights, we'll remove your Madonna, so if you want to hang here, and the people who are keen to hear the answers, you're welcome to stay. Everybody else, coffee break has started already, cigarette break, all sorts of breaks. We are meeting here again at 11:15. We'll be hearing from the fabulous Lisa Atkins. She'll be joining us online as she's in the States. So see you in a short while, or stay here if you want to continue the Q&A session in DUBRAVKO. Thank you.